Good afternoon, or morning, or evening, depending on where you are. Welcome to this month's CWNP webinar. We're going to be talking about 802.11ax, what's new. And of course, I know none of you were looking just a moment ago when I changed it from AC to AX. Don't worry, the other slides talk about 802.11ax. That's just an old habit of what you type, right? So my name's Tom Carpenter. I'm the CTO at CWNP. And this is, I guess, what I would call a high-level webinar, maybe a 100 level, if you will. We're not going to get into extreme, intricate details of each of these new capabilities. We're going to talk about it from the perspective of what they offer and how it might impact our networks, when we might begin to see benefit from some of the features and capabilities and things like that. We'll probably, over the period of the next several months, do some in-depth webinars on many of these topics. So for example, we may take an in-depth look at OFDMA. We'll take an in-depth look at things like BSS coloring and target wake time and so forth. So over the coming months, we'll go much deeper into each of these things. But I wanted to get started giving you information about 802.11ax. Of course, as always, if you want to tweet about the webinar, you can hashtag CWNP webinar, and you can follow us on Twitter. CWNP is at CWNP, and I am at Carpenter Tom. So let's talk about some news. First of all, Wi-Fi Trek registration, of course, is still open. You can go to conferences.cwnp.com in order to learn more and register there. And the call for speakers is still open at this time. It's uncertain how much longer it will be open. So if you're interested in giving a presentation at Wi-Fi Trek, make sure you get in there and submit that call for speakers form. CWAP and CWDP development processes have started. We have started working with several different subject matter experts, arranging times and schedules and when they can help develop different parts of the learning materials and exam and practice tests and so forth. And the new learning materials will be available in late September in their final form, and the new exams will be available on October the 1st. The current exams will be available until October 31st. So just know that there will be about a 1-month overlap there, and then the old CWAP and old CWDP exams will no longer be available. This is very important information. If you're just beginning your studying process right now for either or both of these exams, and you think you're going to take 7 or 8 months, well, keep in mind the current exam, which is what all the current study materials are based on, will be gone as of October 31st. So you'll want to speed up that preparation if you want to take the current exam sometime before that point. Okay, so let's talk about the new capabilities. First of all here, just in summary, and then we'll look at each of these in a little bit more detail. So first of all, 802.11ax goes back to being a dual band physical layer. So like 802.11n, which operated in 2.4 or 5 gigahertz, 802.11ax has support for 2.4 and 5 gigahertz. Now this is important because 802.11ac, of course, was 5 gigahertz only. Certainly some vendors did implement something like 256 QAM or something of that sort down in 2.4 gigahertz, but it really wasn't part of the standard. So the standard was that 802.11ac stuff worked only in 5 gigahertz. And now with 802.11ax, it's pushing it into both. And there's a big reason for that. The main focus of 802.11ax is really not to make it faster. In other words, to get a bigger pipe. But instead, the main focus is to make it more efficient, whatever the size of the pipe. And so, yes, it does extend the size of the pipe. We'll see that later on. There are higher data rates. For example, if you compare a 40 megahertz channel, 802.11ac, single stream, to a 40 megahertz channel, 802.11ax, single stream, then the AX capabilities are higher. Okay, so the pipe is bigger as far as the data we can push through it. But the main goal is efficiency, which can be a benefit to 2.4 gigahertz in a big way. But we'll talk about realities of that in a moment. We also have OFDMA, orthogonal frequency division multiple access. And so here what we're doing is taking the concept of OFDM that we've had since 802.11a, right, all the way back in 1999. So we take this concept of OFDM and we say, instead of using all of the frequency bandwidth for one frame, one communication, let's allow for sub-channelization, I like to call it, which means we're going to use these things called resource units and allow for multiple different transmissions to go out at the same time. So effectively, you can think of it kind of like having a 2 megahertz channel or a 4 or 8 megahertz channel or what have you. But again, they're not technically called that in the standard. The standard refers to them as resource units or RUs, and they can be as small as 26 subcarriers. So one resource unit, 26 subcarriers, 2 then would be 56, right? Or 52. And so the point is that you can break the channel apart into these resource units, allocate resource units to different devices, and then transmit to those multiple devices concurrently. We also have BSS coloring. BSS coloring doesn't mean that if you use a spectrum analyzer that the signals from one BSS show up as a different color as the signals from another BSS. I know we might like to think it's that way because a lot of our Wi-Fi scanners show each BSS with the little line that shows the OFDMA signal pattern in a different color for each AP that it detects offering that BSS. But that's not what we're doing. We're not changing the color of the RF. We simply have a tag in the frame that is saying the color of the BSS. So you can think of this as color, number, because let's be honest, all computer data is just ones and zeros, right? All computer data is just ones and zeros. So if you want to think about this as my BSS is this series of bits and your BSS is this series of bits, that's what it really is under the hood. But the concept of coloring makes it simpler. So I can say I have a red BSS, there's a green BSS, there's a blue BSS, what have you. We'll talk a little bit more about that. And then we have finally target wake time. Target wake time is a power save / efficiency feature of 802.11ax. Now, I'm not saying that this list is all of the new capabilities in 802.11ax. There are so many that, of course, if I listed them all, we would spend the 30 minutes just getting a 30-second overview of each one of these. So rather than that, I've picked some of the major new capabilities, and we're going to talk about those now in a little more detail. So 2.4 gigahertz lives on. Is it a zombie? Is it only alive for a period of time? Is it something that's going to thrive in the future? I'm not going to answer those questions here today. There's a lot of opinion around that. But I will tell you, it lives on. And not only does it live on because of 802.11ax, 802.11ax supports it because it lives on. And that's the important thing to keep in mind. So 2.4 gigahertz didn't go away. Vendors have continued to provide 2.4 gigahertz and even 2.4 gigahertz only devices. So it's not just that they've continued to support 2.4 gigahertz if you want to use it, but a lot of devices are still manufactured that are 2.4 gigahertz only. Now, granted, many of these are in the consumer space, and there's a big motivation for 2.4 gigahertz support there because so many older Wi-Fi deployments in homes are 2.4 gigahertz only. And so if they sell you a garage door opener that gets on Wi-Fi or a door lock or a grill or whatever it is, and it's 5 gigahertz only, you're in trouble. So they've got to at least make them dual band, or they can say, 100% of our clients in the consumer space support 2.4 gigahertz, or at least it's pretty close to 100%. And therefore, if we buy this cheaper 2.4 gigahertz only chipset, it's not going to hurt anything from the ability of these users to connect. So for those reasons, there's kind of a financial motivation for them to keep doing a lot of 2.4 gigahertz only stuff. Now, even without 11ax, wireless LAN designers and administrators must continue to support 2.4 gigahertz in nearly all installations. It's a rare enterprise deployment where you can do 5 gigahertz only and just not deploy 2.4 gigahertz at all, because there are older devices, there are even newer devices that customer wants to use, and they operate in the 2.4 gigahertz space. So the real world we live in says we don't like the 2.4 gigahertz frequency band. And by the way, it's not that we don't like it because it's somehow inherently bad to be at that frequency level. If we had from, say, 2.4 to 2.8 gigahertz, and we had all of that frequency space, guess what? We probably wouldn't have that many frustrations with it. The problem is it does travel further, generally speaking, than as far as receptivity. It is able to be received at greater distances, let me say it that way, than 5 gigahertz, and certainly than 60 gigahertz. And so that makes it more challenging when you have fewer channels that you can deploy in a staggered channel plan or a multiple channel architecture and end up with as little CCI as possible, co-channel interference. So that's the big point there, right? Well, the coloring, BSS coloring, may help with that some in 802.11ax. Time will tell when we get actual implementations and see what kind of pain points it might create. In that you will have to certainly fine-tune the carrier sense parameters for the overlapping BSS to make sure that there's not unintentional interference being caused. Or, imagine an AP is about to transmit a frame. It sees a frame from another AP and another BSS. It's below a threshold, so it says, okay, I'll go ahead and talk. But that transmitting AP has an output power level that's 50% higher than the OBSS AP. All of a sudden you run into a situation where there could be some significant interference issues there. But we'll talk a little bit more about that when we talk about BSS coloring. Just know for now, it may be something that can help us in the 2.4 gigahertz band. It does provide enhancements to the Mac and Phi that give us greater efficiency. But I've got a big bold point here: when it is available in clients. Now, why is that a big bold point? That's a big, bold point because it doesn't matter if you replace every AP in your environment with 802.11ax APs if none of your clients are 802.11ax. The reality is that, yes, those APs might be able to use some features like BSS coloring to ignore each other's AP frames that are being sent downlink from the AP, but there's really not as much benefit, and almost none, to go to 802.11ax in the infrastructure when your clients don't support it. Now, some might argue, well, you can get some enhancement through maybe the fact that the AP supports more spatial streams than your current APs. True, there is the possibility of that. But the enhancements there are so minor, they don't usually justify the cost of an upgrade. So let's go ahead and talk about the next thing, and that is OFDMA. Now I'm going to keep this at a higher level in order to kind of simplify the learning curve as we move into this learning about 802.11ax. Later on in other series, we'll deep dive into OFDMA and look at all the details. So let me get you thinking a little bit about it now, and then in the future, we can go deeper to look at all of the ways it works. So I've got 3 different slides here that are going to help us understand some of this. And I think it'll give you that big picture view that helps you understand the benefit of OFDMA. So OFDMA really was time domain only. That is to say, if I had a 20 megahertz channel in the frequency domain, each frame used all 20 megahertz of that channel. Now, of course, I don't want to make it too confusing here by bringing in some other details, but if you have a 40 megahertz channel, as you probably know, some clients that are only 20 megahertz capable will transmit only 20 megahertz of that, but the other 20 megahertz just isn't used. So it's not that that other 20 megahertz is used for something else at the same time in the current iterations of 802.11 through 802.11ac. We do have dynamic bandwidth operation with 802.11ac, but even with that, all it does is allow you to figure out which 20 megahertz chunks are free in, say, an 80 megahertz channel, and then you can use either 80, 40, or a 20 megahertz channel width for your transmission, but it's still only one transmission, right? A separate AP could possibly be using some of that 80 megahertz of bandwidth with DBO, but within one BSS, you're using a 20, 40, 80 or 160 megahertz channel, that's what you're using, right? So you don't really have this option of slicing up the frequency domain. So different users within that channel can talk using smaller ranges of bandwidth at the same time. Notice with OFDMA on the right, that is what we do. We still exist in a time domain. Somehow we've not found a way to get out of that yet. So everything still happens in time. I suppose that maybe there is a point in the afterlife where we may be out of the time domain, but right now we're in the time domain. So everything happens in the time domain, whether it's OFDM or OFDMA, but within the time, you can have more than one user communicating within the assigned channel. So if it's a 20 megahertz channel, you could have user 1, 2, and 3 all communicating at some point at the same time. Okay, so I'm not assuming that these are single frames represented here with user 1, 2, and 3. They may be multiple frames, but the point is that at some point in time, user 3 can start talking, and then user 1 can join in, and user 2 can join in. This can be sliced up generally at the frame level in order to allow this communication. Now, there's some complexity in this scheduling and resource unit assignment and so forth that we'll get into in later webinars. This is to get you started thinking. Let me take this to an even higher level. Okay, here's the way 802.11 works now. I was just sitting back the other day and I was trying to think of what's a good analogy of the way the distributed coordination function and even EDCA from 802.11e really works in Wi-Fi today. And, you know, we hear things, well, it's not like a switch, it's like a hub. One thing can talk at a time. And I got to thinking, yes, but it is this, it's distributed coordination function, right? DCF. It's a distributed coordination. And I thought, what is the thing in life that's so much like that? And really, it's like a shared lane where parking is allowed. Now, you've probably all driven on these where you come into an area of a city and you've got a street that is not one way, it's two way, but people can park on the sides. And because of that, quite often there are spots where there's only room for one car to get through, right? So what do? You pull over to the side because you look ahead. Distributed coordination. You look ahead and you coordinate with who's coming. And if you're nice, you might pull over even more than other people do. But the point is, you might have this nice blue sports car that can really kick it at high speeds. In other words, this is an 802.11 AC or AX device, right? But then we've got a couple of 802.11, I don't know, let's pretend they're B devices that are coming down the street. And they've won access to the medium. So one is going through and then the other is going through. And I have to just sit here and wait, regardless of the power that I have under the hood. I can't do anything about it because we have a distributed coordination function. So this is really the way 802.11 works now, where each of the devices, in this case cars and humans in them, that needs to use the channel have to look to see if anyone else is already using it. So our blue sports car on the left looks down the road, sees the silver car already coming through, and knows it cannot talk. And then after the silver car goes through, it looks again and it sees the yellow car coming through, and it knows that it cannot talk, or in this case, drive, right? So once it's clear, then the blue sports car gets to go. And there's no real scheduling. Meaning that if another red car or something comes in behind the yellow car and nudges in there real close, and before the yellow car's out, gets started down that lane, the poor blue car's still stuck there, waiting, regardless of how powerful it is, because it's just not winning the lottery on this shared lane. So this is the way 802.11 works now. One channel, one frame can be on that channel at a time within a certain signal strength range. And because of that, the different devices have to look for each other to see if someone else is talking before they can talk. This is 802.11 today. Okay, so what does 802.11 look like in the future? Well, let's see. So this is the way 802.11ax allows communications. Now, that's phrased very carefully. The way 802.11ax allows communications. I say it's phrased very carefully because just because you have 802.11ax APs does not mean you're going to get this. That you can be transmitting and that you can be receiving in multiple lanes, if you will, right? So you've got multiple lanes of communication instead of a shared lane. And therefore, multiple devices can be receiving or sending communications at the same time. Now, it allows this, but there has to be enough 802.11ax stations to accommodate for it and let it have any real significant impact on your network. And we're not going to be there next year. We're probably not going to be there the year after, in 2020. So this is something down the road we're eventuating toward. We're moving toward this improved method of communications, but we're certainly not going to be there anytime soon. Even though I know in the consumer space, we've got some draft devices that have come along and we're going to see more enterprise and consumer APs later this year. We'll see clients start shipping with them maybe late this year, early next year. All of that's real. I get it. But people don't just rush out the moment a standard is ratified and destroy all of their existing equipment and buy equipment that supports the new standard. It's going to take years. Probably from the time we really have it ratified, I would estimate 18 to 30 months to get to the point where you're getting significant benefit from an 802.11ax infrastructure. So it's going to take a while, and it's going to vary a little bit by industry. It's going to vary by company, depending on what your hardware turnover rate is. How often do you replace laptops, for example, and how often do you replace mobile phones and tablets? That's going to drive a lot of how quickly you can get the benefits from 11ax. Okay, so if you like my analogy, or if you don't like my analogy of the shared lane versus multi-lane, either way, I hope it helps you understand the concept a little bit, taking it to that higher level and understanding what it can do for us. Now with OFDMA, I'm not going to go into excruciating detail about these specs here, but I did want to give you some specs that show where it can be different and the version, if you will, of OFDM that's implemented in 802.11ax can provide some enhancements. So first of all, the subcarrier spacing is only 78.125 kilohertz as opposed to 312.5 kilohertz. So it's 4 times closer, narrower, right? And what that means is since the subcarrier spacing is narrower, we have more of these subcarriers. The symbol time is extended. It's 4 times longer. So instead of being 3.2 microseconds, it's 12.8 microseconds. And then the guard interval. Well, this is interesting because if you remember, it was 800 nanoseconds. And then with 802.11n, we introduced the short guard interval, 400 nanoseconds. And now with 802.11ax, we actually make it longer, up to 4 times longer, 3,200 nanoseconds, or twice as long, 1,600 nanoseconds. And this is all about dealing with intersymbol interference, right? And the various reflections that happen in the environment that can result in poor performance. Modulation, we had 256 quadrature amplitude modulation in 11AC. With 11AX, we have 1024 QAM. And so we have a higher rate of modulation that is available in the right scenario or the right situation. So these are some of the specs, if you're already familiar with OFDM, where things have changed pretty significantly within 802.11ax. Now let's talk a little bit about resource units. So I've mentioned that resource units are used to break the channel apart into multiple chunks that can be used. So you can see that in a 20 megahertz channel, we have 9 resource units. So you'll see RU 1, 2, 3, 4, and RU 6, 7, 8, 9. And then you've got this central RU, which is 13 plus 13, or still 26 resource units, okay? And so basically what this means is that you can have 9 different communications taking place. Or you can break it up differently and have 5, RU1, RU2, RU3, RU4, and then this narrower center. And then you can have the 3, RU1, RU2, and the center. And then you have just, let's put it all together, one big frame that uses all the resource units. Okay, so there are different ways this can be broken apart. There are guards around it, and we do have indexes that indicate what the actual resource units are within the entire 20 megahertz. So there are all kinds of different combinations of this, and this is just 20 megahertz. Doesn't account for what happens when we go to 40, what happens when we go to 80, and so forth. But it gives you an idea of how this can be broken up into those resource units, and then different devices can be communicated with using the different resource units. We also have this BSS collaring that I mentioned. And so if you think about it, then two APs could be communicating, and they're going to have a color set for their BSS in the frame. And this could be, we'll say, red and orange in this case, right? So what happens is our AP on the left transmits a frame. The AP on the right wants to transmit a frame, but it needs to look at that other frame. So it looks at that other frame, it specs the color, and sees that it's orange. And it says, my BSS color is red, and this frame is orange, and below the alternate signal detect threshold, so I will talk. In other words, what I mean by alternate signal detect is that, typically in the past, there's one signal strength that an 802.11 frame could be at for a particular PHY, and the AP had to acknowledge it and not communicate. The client had to acknowledge it and not communicate. Now what we can do is we could say, well, you know what? I'm going to have this allowance to communicate and override that kind of default based on coloring rules, okay? So the way it works then, if you look at the flow chart on the left, is a transmission's detected. The device says that from my BSS, yes, then I have to defer. You always have to defer if it's from the same BSS, just like we always did before. If it's not from my BSS, I'm still not done. I have to say, is the RSSI greater than the carrier sense for an overlapping BSS? So whatever that rule or stipulation is the RSSI greater? If it's greater, I still have to defer. If it's not greater, I can simply ignore the frame and go ahead and communicate as normal. Now, this is where I said, there's going to have to be some things in the algorithms that accommodate for some scenarios here. So for example, we've got the possibility that our AP on the right actually transmits at 3 or 6 dB stronger than the AP on the left. So while the AP on the left sends a frame that is weak enough to not hurt the AP on the right and its BSS, that does not automatically equate to the fact that when I transmit my frame from the AP on the right, I'm not going to cause problems for the AP on the left. So I think you can see this introduces some new potential complexity to things like RRM, which was already complex to understand the algorithms, and to the configuration of this and what configuration options will be available. So it's not an automatic that, oh, there's BSS coloring, everything's going to be better. We have to think through the impact of what this might mean for communications when we go ahead and transmit, even though the frame is seen below a particular signal strength. But remember, that's also even true before, okay? So even before, without all of these BSS coloring rules, we still had that situation where one AP with a higher output power, looking simply at the signal strength received, could be a problem for some other AP that is going to hear that frame louder than it can handle without corruption. So what do we do about that? We have to have the same algorithms in place we do today. Part of it is not algorithmic, it's hardware based. So for example, if within a deployment, all your APs have the same output power level, but we only use higher gain or lower gain antennas to differentiate the coverage area, not the output power level, then that can actually help to solve some of that problem. Okay. The next thing and final major topic I want to talk about before summarizing is target wake time. So target wake time is a new power management option within 802.11ax, but it's something you might not just want to look at as a power save function, but also as an efficiency gain function, because of the fact that it can schedule when communications happen. So it's able to basically negotiate with the client. It can do a broadcast target wake time. It can do a negotiated target wake time, and it can therefore configure when what clients are going to be waking up, right? And so they don't necessarily all have to be on the same wake time. And because of this, we could stagger these wake times in order to get more efficiency. At least that's a theoretical concept. We'll have to see how that plays out in the real world. But either way, still being able to set a target wake time, even if it's just a broadcast method, it results in the ability to more efficiently manage power, really to such an extent that it's estimated that power reductions can be from 50 to 95% using target wake time over current power management solutions. So obviously that can be significant. All right, so let's summarize what we've talked about in today's presentation, and then we'll wrap up with some Q&A for those that want to hang around for that. So in summary, 802.11ac was 5 gigahertz only, 11ax is 2.4 and 5 gigahertz. The channel bandwidth is the same. The difference comes in the fact that 802.11ax supports resource units, AC does not. The subcarrier spacing, as we talked about, 312.5 kilohertz in 11ac, 78.125 kilohertz in 11ax. 3.2 microsecond symbol duration versus 12.8 microseconds, 256 QAM versus 1024 QAM. The data rates then. So with 802.11ac, 256 QAM, we can get 433 megabits per second with one spatial stream and 80 megahertz. With 802.11ax, we can get 600.4 megabits per second with one spatial stream. And I want to point out that that is still 256 QAM. Okay, that data rate is not 1024 QAM on the lower right. So you see that just through the changes in subcarrier spacing and symbol duration and so forth, we can push the data rate higher with 802.11ax. Okay, so that's the scheduled content that we had to cover today, and we're ready for Q&A, which will not be archived at cwnp.com.